afternoon, Rohan, Ronak. I'm audible. Uh, so the slide is visible. Just a minute. Okay. Not. It's problem. But the slide is visible, na? Slide is visible, na? Okay. So we started this fiber bracketing. It is based on the grating that is written within a fiber. To understand this fiber bracketings, you should know the grating, simple grating. Simple grating, it can be reflection gratings, or it can be mentioned. It can be transmission grating, reflection grating, or can be transmission grating. Transmission grating. I mean, in the reflection gratings, incident and refracted beam will be the same side, whereas in the transmission gratings, incident beam and refracted beam on the opposite side of the gratings, right? But anyway, for both these gratings, there will be groups will be there. I mean, opaque, transparent. This type of groups will be there, and you see when light incident here, then it will be diffracted. Say if two wavelengths are there, then two wavelengths will be at different wavelengths. It will be diffracted. Right. In fact, it follows the constructive interference of the grating equations. That is this one, capital lambda times sine theta I minus sine theta D equal to m. That is the diffraction relations for incidence angle theta I, and theta D is the diffraction angle. Is same as for transmission grating as well as reflection gratings. M is the order of interference, first order, second order, third order, like these things. But fiber bracketing, for bracketing, generally m equal to 1. I told you it will be plus minus 1. That is the fiber bracketings. For bracketings, only one order will be present, right? And back condition is there. I mean, if back condition is there, then if you say this actual grating will be said, this is a clad, this is core. Within the core, grating structure is being created. How it is created, we'll see it. So when you use some broadband light here, I'll just show you. Then you see if the Bragg condition is satisfied, that is lambda b equal to twice an effective capital lambda. If the Bragg condition is satisfied for a particular wavelength, then that wavelength will be reflected back, right? And in the transmission side, you will get some, you see, some dip will be there, and in the incident side, from where the source, the light is launched, that times you'll get a reflected wavelengths, right? So the transmission spectrum, this is the reflection spectrum, you'll get it, right, in the bracket. That means it will act as a filter. Not only it will act as a filter, also it can act as a multiplexer, demultiplexer, like these things, add-drop multiplexer, I told you. Many applications are there, right, the fiber bracketings. I told you for modern 5G network, it is now fiber grating is an essential element for the for different networks, different network configuration, like say LAN, MAN, WAN. Even in the LAN also, there can be mesh, ring, star, etc. So on all those cases, fiber bracketing is an essential element. Well, you see it here. What are the advantages if you have this grating? Then what will be the advantages? Uh, Advantages will be it has very low. It's all fiber gratings. So for other filter, if you use it in between fiber, then loss will be there. But here it's the same as the fiber. Same communication fiber. Within the communication fiber, one portion will be the fiber bracketings, right? So it is the same dimension as the fiber, the communication fiber. So compatibility is here. That means it will be very low loss and also low cost will be there, and easy of coupling with the other fibers will be there because the same dimension just I mentioned. Polarizer insensitive, low temperature coefficient, and simple packagings. So these are the distinct advantages of fiber packagings, and basically it is used in DWD systems. So this is the modern technology for optic communication systems. Dense wavelength division multiplexing. So wavelength multiplexing, we have seen it, but dense wavelength multiplexings, there will be more than 16 wavelengths. Generally, 16 to 100 wavelengths can be there, right? So these are the advantages, and it's based on this the grading equations. And if first you see before going to the details of it, you see how grating is being fabricated within the fiber. In fact, the conventional single mode fiber is here, but it is photosensitive using some doping. So germanium, some photosensitive materials is doped. Next, ultraviolet laser is used. Then, if you use it to ultraviolet beams, then it will create interference pattern. And in that pattern, if you place the fiber, interference means you see instead of you'll get dark by fringe pattern will be there. Somewhere you get bright intensity, somewhere dark, bright, dark, bright, dark will be there. I mean, it will be something like this in this way. So somewhere you get maximum intensity, minimum intensity, maximum, minimum will be there. And so refractive index variation will be there when you use the ultraviolet beams, ultraviolet laser beams, right? And in fact, high intensity regions, refractive index will increase at the where there is dark means there is no light. That times it is a background refractive index. So high low refractive index variation will be there. Based on these things, a grating structure will be created. It is like phase gratings, transmission grating, phase grating. Those things are also I mean, amplitude grating, phase grating. Those things are there. So here actually it is phase gratings, because refractive index variation is here. Then it is called, if refractive variation is here, then it is called the phase grating. So you see actual configurations here. Germanium doped fiber is germanium doped silica fiber, right? Germanium doped silica fiber is here. Silica fiber, and ultraviolet light is used, for which the wavelength it is 244 nanometer. Right. So here you see how grating is written within the fiber. This is germanium doped fiber core. In the core, germanium doping is here. It will be photosensitive. Now, if you use two beams, two laser beams, I mean from the same source, if you create two beams and the wavelength it is 244 nanometer, that is ultraviolet, then it will create a interference pattern. Right, just like this interference pattern will be created. And so just now I mentioned high intensity, low intensity regions will be there. In the high intensity regions, refractive index will increase. In fact, there will be cross-linking of bonds will be there. Bonds formation will be there. Because of this cross-linking bonds, refractive index variation will be there. Somewhere you get high density, low density, like these things. Background density will be there. So different atomic structure will be modified because of this illumination of the ultraviolet light. So accordingly, refractive index modulation will be there, and that modulation can be sinusoidal, like these things. Say you see NZ, that is N core. There is a basic refractive index of the core, plus there could be a variation of sinusoidal modulation will be there. Delta n, the increase in refractive index times 1 plus cosine 2 pi z by capital lambda. Capital lambda is a getting period, you see, getting pitch or getting period, capital lambda. Right. So in this way, you can have the gratings within the fiber, but this grating length can be few centimeter, maybe 1 centimeter to 10 centimeter, like these things. Right, few centimeter. Long period getting, there are different types of gettings are there. Can be a normal fiber getting, it is few centimeter, maybe 10, maybe 1 or 2 centimeters, like these things. Right. And you see, that means here, if you use this interference pattern, then you see refractive index variation will be there. Somewhere increase in refractive index and background refractive index. In core is the background refractive index, and where refractive is increased, that is the ineffective. So like these things. And this is the getting pitch, capital lambda, getting period or getting pitch. Right. So it is mentioned that you can see getting length can be 0.5 centimeter and 5 millimeter, like these things. And for normal FBG, but of course, there can be long period gettings, there can be char fiber gettings, there can be superstructure fiber gettings. In those cases, the length will vary. Right. This is for normal FBG. This is one method. Another method is also there, mask method. It is not mentioned here. Masking. Initially, some mask is there, right? Some mask will be created, and next, when it is illuminated, mask is illuminated, then you see within the fiber, a pattern will be created through the mask. When the ultraviolet beam is passed through this mask, right, there will be this type of interference pattern will be there, right, and similar patterns will be created using mask. This is a holographic technique. This is a mask technique. A mask is first prepared, next mask is illuminated by the laser beams, and next this grating fiber is placed beneath this mask. Then you'll get a pattern, get like this things. You can have it. So there is a mask method is also there. There is a interference technique is also there. In this way, you can fabricate the gettings, and you see if you use a polychromatic light, and if this condition is satisfied, this Bragg condition, the lambda Bragg equal to twice n effective times capital lambda, then you see that light will be reflected back. Right, that light will be reflected. I'll just demonstrate you, show you how light is reflected. So lambda Bragg, depending on the period, depending on the effective index, a particular wavelength will be reflected back. So if you vary this period or vary this one ineffective, then lambda reflection of light also will vary. Particular wavelength will vary, right? So back if if a particular wavelength is reflected, then in that conditions the peak reflectivity Rmax can be it is tan hyperbolic square tan h square times KL. K is the coupling coefficient. L is the length of the gettings. Right, and for sinusoidal modulations, this coupling coefficient, this K can be pi delta n eta by lambda Bragg, where eta it is called the fraction. Wait a minute, it is the fraction of power that is contained within the fiber core. This eta. And this eta is related to the V number of the fiber, 1 minus V to the power minus 2. So these relations are most important. Reflection coefficient, peak reflectivity when back condition is satisfied, and these are Bragg conditions. The particular which wavelength will be reflected, that depends upon this n effective and capital lambda, that is the getting period. This is a coupling coefficient, there's a peak reflectivity expressions. Our coefficient K depends on the increase in refractive index, Bragg wavelengths, and also the fraction of power that is remaining in the core. where eta approximately can be written as 1 minus b to the power minus 2. So these are the important parameters while dealing with the fiber bracket. Fiber bracket is not only used for filtering, multiplexing, demultiplexer, but also this can be used for sensor also. You see, modern day fiber sensor also most important. It's a fiber not only can be used as communication media, but also it can be used as the sensing element. I mean, this getting period or the NFP department can vary and due to physical measurements like say pressure, temperature, strain, current, voltage, etc. So either this will vary or this will vary. Based on these things, with proper calibrations, you can find out the measurement informations. That is sensing applications. Anyway, we'll see since we are dealing with the communications. We'll see how this fiber bracketing can be used as a multiplexer or demultiplexer. You see it here. Here, just I mentioned, this is a fiber bracketing. I told you also, if you use a broadband source, then a particular wavelength will be reflected depending on these brag conditions, and there will be a diff, and in the reflection spectrums, you will get a particular wavelengths. These things that I mentioned. Now see these configurations where it can be used as demultiplexer. See here it is in the input fiber, many wavelengths are there. How can you separate one wavelength? Here you need a circulator. This is a circle, 3-port circulator, 1, 2, 3, and right, 3-port circulator. And the characteristic of the circular is it will allow light to pass only in the forward directions, not in the backward directions. Right. That means it is clockwise, always in the clockwise. So if you launch light, light will be passed through port number 2, not through port number 3. Right. So similarly, when light is entering, if light is entering through port 2, then it will go to port 3. So here actually you see fiber bracketing is placed at the output side here, right? And it is for this the bracket condition satisfied for lambda 2, these bracketings. Then lambda 2 will be reflected back. This is lambda 2, lambda brag equal to lambda 2. Lambda brag equal to, say, if it is lambda 2, then lambda 2 will be reflected back. Other wavelengths will be transmitted. You see lambda 1, lambda 3, lambda 4, they will be transmitted as such. For them, it is acts as a window. So this lambda 2 when is reflected back, then again it will be propagating through the circulators, and it will be coming out of the port 3. So you can have drop wavelengths. Wavelength is dropped. Similarly, if you have another circulator, another grating, another wavelength can be separated out. So that is actually demultiplexer. From individual wavelengths can be separated out. Also, it can be add drop multiplexers. Both adding and dropping is possible. I mean, here it is demultiplexer, or it can be a reverse also. Reverse way it can be a multiplexer also. From this side, lambda 1, lambda 2, etc. If it is added, then you can have all the wavelengths in the output power. I'll just next configuration see it will be clear. So here actually you see it. Suppose n lambdas are there, and you see circulators, and there are say these gratings are there that for which the say lambda 2, lambda there are 3 gratings are there where lambda 1, lambda 2, lambda 3 are dropped. No, lambda 4, lambda 2, lambda 3, lambda 4. Here lambda 1 is here. So lambda 4, lambda 2, lambda 3, they are you see being reflected. They are reflected and they will be coming out through port 3. At the same time, you can see it here. Some of the wavelengths can be added here, but here there is no added wavelengths. Only here drop wavelengths are there. Right. and these gettings are tunables. You can tune to the fiber bracket is getting wavelengths can be tuned to a particular wavelengths. I mean, lambda brag, just I mentioned just now, lambda brag, that is twice an effective times capital lambda, right? So, tunable means by having this capital lambda means periodicity, you can change the lambda brag. So that's why it is called tunables. By using temperature or using strain, you can change the periodicity. So I can change the parameters. Right. And you see it here. This is so it is demultiplexer. Wavelengths are separated here, but you can added wavelengths also. You can drop wavelengths. You can added wavelengths means multiplexer. Suppose some wavelengths are there, you can add and here it is. Okay, this is lambda 1. Okay, this is lambda 1, lambda 2, lambda 3 drops. So here actually you're getting lambda 4 onwards, lambda n, right? But when you added this 1, 2, 3, 3, these wavelengths first it coming out of 1. Next, there will be these gettings will be tuned to these particular wavelengths, lambda 1, lambda 2, lambda 3, so that these wavelengths will be reflected back. When it reflected back, again it will enter into the 3-port network, but this time it will be coming out of the port 2, 1 to 2. Right, so you get the combination of wavelengths as before. So you can drop some wavelengths. You can see it here. You can add some wavelengths. So the whole system it is called add-drop multiplexing. It is widely used in 5G communication systems. This is the most important um, configurations, important element for optical fiber network. Okay. If you have any questions, you can ask. Anybody, if you have any questions, किसी कोई क्वेश्चन तो पूछो एड्रॉप मल्टीप्लेक्सिंग के बारे में. इससे कोई क्वेश्चन है? कोई एक आध क्वेश्चन तो पूछो. किसी कोई क्वेश्चन नहीं है? यस और नो बोलो. हाँ बोलो, यस और नो बोलो. अरे कम से कम नो तो बोलो. किसी कोई क्वेश्चन है कि नहीं है?
नो सर.
कम से कम नो तो बोलो, तो हम समझेंगे जी तुम लोग सुन रहे कि नहीं. Okay. Next, you see, just see these packetings. Some slides are there. You can see it. So this is the you see this is a fiber within the core. This grating structure is here. Maybe 1 centimeter or less, right? And you see these are back conditions I have mentioned. And you see this is the refractive index variations, refractive index variations, right? This is the grating period. And you see this lesson actually shows you can change the wavelength by changing by using strain. By strain, this periodicity can change. If you give some say pressure, that will create I mean pressure, some pressure or some, if you give some load here, then periodicity will change. This lambda, capital lambda will change. So capital lambda change means lambda brag will change. There will be shift in the wavelength. Suppose earlier it is this ones. So after providing strains, this can be shifted to either in the longer wavelength side or in the shorter wavelength side. Right. There will be shift in the wavelength. That is called delta lambda. So that is a delta lambda actually. Okay. Just see it, how it is being. I think now quite clear. Suppose from this side, you are using this many of colors, right? Multiple wavelengths, right? But here you see this if it is the black condition satisfied for this blue violet, then I see violet color is reflected back. But other lights are being transmitted as such. You can see there is a dip in the violet color. Other wavelengths are transmitted. So here I think it is quite clear now how the bracketing operates. Right. You see other colors are there. In this case, here it is red. You see, this is the red ones. By changing this periodicity, you see, black condition can be changed. So accordingly, reflection of light will be different. So this is the spectrum input source, but after using reflection spectrum will be only these ones, and the transmission spectrum will be these ones. Okay, this is the fiber bracketing, and it can be of different types. I told you, it can be normal gettings. It can be sharp getting. Sharp getting means here you see getting period is constant, but here getting period can also vary. You see it here. So that is called sharp gettings. Or sharp gettings. Also, it can be long period gettings. This periodicity is quite large. Both are showing same intensity, but I mean, this long period getting will be same as this one, but this length can be few centimeters, maybe 10 centimeters in length. That is long period getting. Sharp getting it is actually these ones where spacings are different. Here see here one kind of spacing is here, but here different kind of spacing is here. So there is a nonlinear variation is here, right? So that is a sharp fiber gettings. Tilted fiber gettings, it can be tilted like these things, right? Superstructure getting is this is another most advanced type of ABG where in this getting length, if this is a total getting length, say this is the getting length, within the getting length, also there can be variation like these things. Getting, there is no getting, no getting, like these things. Then you see, you can have superstructure fiber bracketings. Important is this here. Say useful, very useful for sensor. I mean, with the same greeting structure, you can measure 3-4 measurements. Like say, the same time you can measure pressure, temperature, humidity. 3 parameters can be determined using this superstructure fiber bracketings. So that is no need of different sensors. Same structure can be used to measure more than one parameter, multi-parameter sensing, you can say. So this is the superstructure gettings. Okay, another important passive element is here, which is called the arrayed waveguide gettings, arrayed AWG, arrayed waveguide gettings. Arrayed waveguide getting, which also can be used for multiplexer, can be demultiplexer, can be add drop multiplexers, can be wavelength routers, right? So various applications are there for arrayed waveguide gettings. In fact, it is based on this Mach-Zehnder fiber interferometer. Mach-Zehnder interferometer is a closed interferometer. You can see it here. Say there are two. It's a fiber interferometer. It's a two couplers. There are 2x2 coupler. You see there are. This is 2x2 coupler. We have seen it. There is another 2x2 couplers. Right. Actually, regular directional couplers. So two 2x2 couplers are there, and they are connected here. See it. They are connected. So that will form Mach-Zehnder interferometer. In this Mach-Zehnder interferometer, so if you launch lights here, lambda 1, lambda 2, then at the output ports you'll get lambda 1, lambda 2 with the phase variations, right? And in this case, the path difference is the most important between these two, delta L. That is the delta L, right? Which wavelengths will be which ports, that depends upon this the path difference between the two arms. That path difference actually is 2 pi by lambda times phase difference delta, that will be 2 pi by lambda times path difference in delta L. Right, refractive index time, these ones. Phase difference. So based on this phase difference, you can have different wavelengths or maybe same lengths with different power, like these things. Right. And so this is Mach Zehnder, and array wavelet getting consisting of several such Mach Zehnder's. You can see here there are two star couplers are there, two star couplers are there, and in between some Mach Zehnder, different Mach Zehnder's are there. Right. In there'll be these wavegates are there. Right. It can be a fiber also. This can be an optical fiber also. Just a minute. Mhm. And this N uncoupled wavegates can be there in the central regions. The two star couplers are there, and there can be just Mach Zehnder type. There here only it is showing two many such Mach Zehnder's will be there. So you can say Mach Zehnder gating also, you can say Mach Zehnder type gatings, right? And it can be used for multiplexer, demultiplexer. For multiplexer, input can be n numbers and output will be one. Right, at the output, only one output port will be effective in that case. Right, that is the multiplex. Demultiplier is what's here. Input will be one and output can be of n types for demultiplexers. Right. So that is demultiplexer, and for another easier for focusing or for routing. Then for routing, and it can be m input equal to m output. I mean, both can be equals for routing in the informations. So it can be different types. It can be multiplexer, it can be demultiplexer, it can be routings, routers, etc. Right. And you see there how actually light is being coupled here. You can see it here. It is based on the actually simply the star couplers. They behave like lens. You see it here. So this is the input-output waveguides, and this is the waveguide array in betweens, right? And this will act with star coupler at a length of focal length LF, and this theta. You see theta is the incidence angles. Just a minute. Mm. 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 Here, the length difference delta L, length difference delta L. So one object to another object, Mach Zehnder, just Mach Zehnder types. So that delta L, the phase difference, the 2 pi by lambda times path difference, that is NC times delta. NC is the refractive index of the waveguides, right? And the getting equations, it will follow the getting equation actually. So that is NS d sin theta plus NC delta L equal to m delta. Theta is the angle of incidence, right? Angle of incidence, you see it here. So this one, the getting equations, and m the order of diffraction order of the gettings. Focusing can also be obtained since lens. So focusing property can also be obtained if it follows these ones. If delta L equal to m into lambda c by nc. That lambda c is the central wavelengths. That is actually the central wavelengths. That is, you can say, pass wavelengths from the center input waveguide to center output waveguide. The lambda c. NC, I told you, that is the refractive index of the waveguide. One reflectiveness of the waveguide, and this NS is the reflectiveness of the star couplers. Right. They are the waveguides and they are the star couplers. So NS is the reflectiveness of the star couplers. And D is the spacing among the waveguides. Spacing among the D. The spacing among the waveguides. Delta L is the path difference between two adjacent waveguides. So with this, you can determine the channel spacing also can be determined for such device. So channel spacing, how can it do channel spacing? If you know the angular dispersions. So angular dispersion, just like prism is d theta by d nu or d lambda, you can also do it. That for this case, it can be written in these forms: m minus m lambda square ns cd times ng by nc. M the order of interference that we know it. Ns reflectiveness of the star coupler, C velocity of light, D the spacing among the waveguides, N the group reflective index, and Nc is the reflection of the waveguide. Group reflective index, it can be in these forms: Nc minus lambda dNc d lambda. So the channel spacing in terms of frequency delta nu, that is actually x by 2 LF. LF is the focal length. Star coupler of axial length, so it's the x by LF d theta by d nu all to minus 1. So if we just put this one, so you'll get this is the expression for channel spacing delta nu. Or in terms of lambda, it will be x by LF NSD by M into NC by NG, and which is simplified in these forms. So that is the channel spacing in terms of delta nu or in terms of delta lambda. In terms of frequency or in terms of wavelength of light. Another important factor is also there in these configurations, that is free spectral range. In fact, here it is, if you see, it is periodic. Here it is periodic. Maximum will be, since the diffraction is here in the star coupler, so it is periodic among the maximum. So one parameter is also used in array waveguide, that is a free spectral range FSR. That is actually the period between two successive maxima. So that is actually delta nu FSR. That is actually C by Ng delta L plus d sine theta I incidence angles. Now here is incident angles, that is the diffraction angles. D sine theta I plus d sine theta 0. Theta 0, theta I, both are diffraction angles. One is the input side, another is the output. There are two star couplers are there. So one at the input star coupler, other is other output star couplers. So theta I actually x by LF, and another is this theta 0, it is kx by LF. LF is the focal length of the star couplers. That it will behave as lengths. Now this can be simplified if you consider the input port output ports across each other, then the theta I, theta 0 will be 0, right? And in that case, if this will be 0, so in that case, delta nu FSR will be C by Mg by twice. So that is the free spectral range, the period between two successive maxima, successive field maxima in the frequency domains. So this is also used to characterize the array waveguide gratings. So these waveguide gratings can be used for you see, for multiplexer, demultiplexer, router, etc. I say it has wide applications. So basically, it is based on Mach-Zehnder types interferometer. Per Mach-Zehnder, it is only two waveguides are there, but an array of waveguides will be there. Right. So that is in the array waveguide gettings. इससे समझ में आया कि नहीं आया बताओ. This is this array replicating, how it is, how does it act as multiplexer or how does it act as demultiplexer? If you have any questions, you can ask. तो किसी का क्वेश्चन है तो पूछो, किसी का कोई क्वेश्चन है तो पूछो, और ना तो नो बोलो। क्वेश्चन है कुछ तो नो तो बोलो, नहीं है तो सो के उठ जाओ एक बार, नो बोलो एक बार, यस सर नो बोलो, कुछ तो बोलो। नो भी नहीं बोल सकते हो, अरे कुछ तो बोलो। तीन चार आदमी कितना है? इतना सारा है प्रहलाद, यू आर लिविंग एंड ज्वाइनिंग प्रहलाद, प्रहलाद अनम्यूट, प्रहलाद अनम्यूट, प्रहलाद अनम्यूट इट, अनम्यूट योरसेल्फ, प्रहलाद अनम्यूट योरसेल्फ। बात ही नहीं सुन रहे। रौनक, रोहन, विशाल, कोई सुन नहीं रहा है। विशाल, प्रियांश, कोई आवाज भी नहीं दे रहा है। हाँ विशाल, प्रियांश,
सर
सो गए थे क्या? तब से हम पूछ रहे हैं। अनम्यूट योरसेल्फ, अनम्यूट योरसेल्फ। हाँ, सो गए थे क्या?
नो सर
चल
हो
दिए थे
रहे
कहाँ? हाँ,
नहीं
आज
सर
क्या
यही
क्या
पढ़ी
पढ़ाया बताओ तो। हाँ, क्या क्या पढ़ाया बताओ तो, क्या क्या बोले हैं अभी? विशाल
अब
बोलो
अरे
बोलो।
वेबसाइट रेटिंग के बारे में पढ़ा रहे थे, शायद उसको को कपलर्स के बारे में पढ़ा रहे थे वही सर।
वही सब। हाँ, फाइबर ब्रैकेटिंग नहीं पढ़ाया। ठीक है, नेक्स्ट टाइम उसे ऑप्टिकल एम्पलीफायर पढ़ेंगे। ऐसे करते रहो, आराम से निकल जाओगे। ऐसे सोते जाओ, सोते रहो, और एंड सब में भी सोते रहना। यहाँ पर हम लोग बिस्तर रेडी कर देंगे, आकर के बिस्तर में सो जाना। ओके।